All right, ladies and gentlemen, here we are. It's a Wednesday at 4 o'clock Eastern. That's not our normal webcast time, but it is time for Special Edition. That's right. My name is Eric Cavanaugh. I'm going to be your moderator for this very interesting and compelling story we have for you today. We're going to talk all about the algebra of data. That's right, folks. It's back to school. A foundation for the data economy is what we're talking about. This is really neat stuff. Our good friend Dr. Robin Bloor, Chief Analyst here at the Bloor Group, has been head down for some time now working on a book about the algebra of data. You saw it right there a second ago. We're going to talk all about that today. And really it's up to me to give you the context of what this all means. So, of course, math. Everyone took math back in class, or you were supposed to. And it's the cornerstone of everything in the world of engineering if you get right down to it. It helped us build the pyramids. It led to the skyscrapers. We put a man on the moon. Maybe it'll finally solve data management. Well, the beautiful thing about math, if you take a step back and think about it, especially algebra in particular, is that it allows you to express extremely complex concepts in very simple ways. Now, granted, you have to understand the algebra and learn the algebra, understand the functions and understand the symbols and so forth. But once you do, algebra is tremendously elegant. It's so simple. You can show an algebraic expression with a handful of characters that can encompass incredible amounts of information. Well, to date, there has been no complete algebra of data. Robert's going to talk about this a bit, so I won't steal his thunder, but that's what he has been working on, writing about the algebra of data. In fact, if you want a little bit of history, the very first briefing room ever, way back in September of 2010, featured Dr. Robin Bloor and a spokesperson from a company called Algebraically Data. Well, they did the first ever briefing room. That's 5.5 years ago. And after we sold the first one, it just kind of took off, and we've been riding the wave ever since. But in the last year or so, they've been working on this algebra of data, or the last 6 months, really, and it's largely because Robin suggested to them, has anyone built the algebra of data yet? Is that part of your product line? And they looked around and they thought, well, we've been building a lot of great stuff, but we haven't really rounded out a complete algebra of data, and that's what they've done. And folks, if you sit back and think about it, think about how painful so many aspects of data management are these days. All the data quality problems, all of the workarounds that are necessary to deal with some of the inefficiencies in the design of information systems and the design of the relational database. Quite frankly, Robin's going to talk about that a bit. And theoretically, this new algebra could help solve a whole host of those problems. So if you really just think for a second about how much difficulty there is moving data around, representing data, integrating data, reconciling data, I'm of the opinion that that reconciliation component is probably going to be the single most addressable with an algebra of data. But we're a long way from making all that stuff happen. So we're a long way from any real elegance in data management thanks to algebra, but the beginning is here and it's coming right now towards us as we speak. So on the left, of course, you see the pyramids. On the right, that interesting set of geometric structures there. Well, that's also in the Middle East. That's actually a Syrian refugee camp in Jordan, just proving that algebra can't solve everything. So with that, I'm going to introduce Robin Bloor, our Chief Analyst. You can find him on Twitter and as yours truly as well, at Eric_Cavanaugh. And you can always email me as well. The dark web, some kids call that email. I think that's a bit strong. But anyway, with that, let me hand it off to the man who has been head down for months writing this book, folks. Wow, what a piece of work, what an accomplishment. Dr. Robin Bloor, the floor is yours.
Okay, well, thanks for that introduction, Eric. This is the first time I've ever presented mathematics in a webinar, but I'm not really going to spend a whole heap of time talking about the math. I just want to kind of, in one way or another, demonstrate that it's real. And probably the best way to start is the backstory. You know, what happened when we first encountered algebraics I think it was about 5.5 years ago, was that they were initially in the process of building a relational database optimization capability. And I went in and talked to them, but what actually happened, I think, because it was necessary, really, in terms of them to substantiate their claims. It was necessary for me to actually speak with a mathematician, and the guy who was there, Gary Sherman, is the guy that I've written this book with, Professor Gary Sherman. Gave me a maths lessons one afternoon, and I was actually incredibly impressed simply because he's actually a really good math teacher apart from anything else. And then a lot of time has gone by, and at the beginning of the year, Charlie Silver, who's the CEO of Algebraics, called me and asked me if I would be willing to participate in the writing of a book about data algebra. So over a period of about 5 years, Algebraics has in one way or another done a fair amount of exploration of data algebra, lodged a number of patents, and decided that it was time to actually unleash this on the world. So that's really what this is about, aside from the fact that we wrote a book. The first point is that there's never previously been an algebra of data. And we perhaps should be surprised by that. And really, the main reason for that was it was tried before and it didn't work. It went astray is probably the best thing to say. The initial approach, following work by Ted Codd, met the light of day. It had been done in the 60s and met the light of day in 1970 when he published a paper. And for a period of about 5 years, and I think most of the work took place at IBM, but for a period of about 5 years, there was development work on that. And as far as I can tell from the early mathematics, it certainly began with the best intentions. But it actually never ended up providing a mathematical basis for data, and it subsequently went off the rails. And I'm going to kind of explain why that happened, because if you kind of look around and you think about relational database have just been let's say, a dramatic contribution to the whole of the IT world for the best part of 3 decades. So it isn't that relational algebra was inherently ineffective. It actually proved to be quite effective for data held as tables. It's just that it actually wasn't mathematical. They departed from it being an algebra early on. The way that happened, really, I mean, most people don't even know what an algebra actually is, Fundamentally, an algebra is a set of operations on a field of numbers, mainly, using specific structures. The problem that occurred with the relational algebra was, first of all, it wasn't established axiomatically. There was basically, people went around saying it was based on set theory, but actually it wasn't based on set theory. They never defined what a basic element was. There was no definition of the genesis or the ground set from which elements would be extracted. There was the abuse of the mathematical term relation. A relation isn't what is called a relational database. A relation is a table in a relational database. A relation is actually a set of couplets formed from 2 sets. So it seems clear to me, but it's very difficult to say because you'd have to have been around at the time. But it seemed to me that actually what happened with relational algebra is it lacked mathematical rigor from the get-go. And then in 1975, SQL was invented. And the decision that was taken around SQL was to actually treat all data as data living in tables. Therefore, they'd ceased to be mathematical in any strict sense of the word, because they had actually started to invent a set of operations around a visual artifice, table being the visual artifice. In order to actually make that work, they invented something called a null. Right? And that's something that exists and yet doesn't exist. And actually, mathematically, it's nonsense. You can't have, it's a kind of kludge to make things fit in tables, because if something isn't there, in order to retain the structure of the table, you declare it as being null. But the null doesn't actually have a value, and it isn't a value. And the truth of the matter is if you've got nulls in things, you aren't in a table anymore. You're in a data collection, you're in a set of relations, but you're not in a table. And as a consequence of that, relational databases constrained to tabular data structures. And it worked very, very well for those tabular data structures. And most of the operations that are carried out on a relational database, aside from the various things that were introduced to try and force things into tables, worked really very effectively. But because it didn't cover all data, you ended up with a variety of alternative databases. They've gradually emerged over time. I mean, some emerged fairly swiftly. In actual fact, there were some object databases, for instance, but they tended to be niche. Now we've got what are actually still object databases, but called document databases, and they have become extreme amount of use. And then we get, you know, if you have developed software for relational databases, there's something called the impedance mismatch. The impedance mismatch is based upon the actual reality that when you're actually programming something, you end up with a result that could reasonably well defined as an object. And nowadays, most people who are developing treat data as objects. But objects don't fit into tables. So that's really the impedance mismatch. Relational databases cannot accept valid structures, anything that isn't tabular. So that's kind of what happened, right? And what the algebra of data does is it makes all that go away. If you want to have data in tables, yeah, sure, you can have data in tables. And if you want to have other data structures, sure, you can have those. And basically, I'm not going to prove that, but I'm just going to talk around it because I actually wrote a whole book to prove that. Something that's worth saying, nobody is going to dispute data algebra from a mathematical perspective because there's actually no new mathematics in it. What has actually happened is that set theory has been taken and used in the way that set theory has been used for decades in one way or another to define distinct algebras. And the only errors that could be in it is if those definitions of those algebras were actually incorrect. And as far as I can tell, they're pretty much perfect. And it would be easy to spot an error from a mathematical perspective. So, you know, data algebra is very interesting in the sense that it defines what data can be and how you can define data and how you can define data structures. But there's no new mathematics in it. It's just a set of representations that are not wildly unusual in mathematics. The background, the Algebra of Data, the Algebraics Data Corporation financed research into data algebra. That was the reason that the company was set up, and the reason that the various investors put money in. They all bought the idea that a mathematical basis for data could be created, but it didn't exist at the beginning. There's a certain leap of faith by the investors. The algebra was conceived and can be wholly attributed to Professor Gary Sherman. He was engaged by algebraics for the specific purpose of proving out a formal mathematical approach to data. The way that was done, aside from actually the initial mathematics, you know, the initial application of set theory to data, was to actually take fairly hard problems in the sphere of software and test the algebra against those problems. So it was tested on an informational relational database, and it's been tested on an implementation of an RDF database. that is a triple store. And it's been tested against all possible forms of graph, and as far as I can tell, it's been proven against almost all data structures. And I'm using the term almost all because there is within data algebra itself, there is a means of developing any possible data structure that you actually want. But when you get extremely complex sets of sets of sets of sets of sets, that kind of complexity, it's only been, the algebra here has only been tested against its use in software up to 4 levels of sets, so sets of sets of sets of sets. The belief is that it would just continue to go beyond that because the movement from sets of sets to sets of sets of sets was reasonably smooth, and there's no mathematical reason to believe it would be otherwise. So what had happened here was that the algebra was being developed in conjunction with a whole set of activities that were going on in data management. And every time the software engineers found a problem, they would bring it to Gary Sherman or one of his assistants, and they would spend time in a whiteboard hammering out a solution. So that all the approaches would have been demonstrated mathematically. And then the software engineers would go away and do something else, and so on and so forth. So it has been proved to have multiple potential areas of application in the sense that it's been demonstrated for data management, it's been demonstrated for query optimization, and it's been demonstrated for data integration. And that's the kind of backdrop. So after that kind of work was done at in March of this year, Charlie Silver, CEO of Algebraics, approached me and asked me if I'd like to write a book in conjunction with Professor Gary Sherman. And that's what I did. So, it's not, and if you're not familiar with mathematics, it's not really easy to understand exactly what is going on by creating an algebra within an algebra within an algebra. But, you know, data algebra, the basics of data algebra, the thing that makes it powerful is actually 3 interrelated algebras, and they sit within one another like Russian nesting dolls. The way the easiest way to think about this is to think about the natural numbers, you know, the numbers that you count with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on forever. And there are a number of operations that you can use on the natural numbers. You can use addition and you can use multiplication. And if you do that, you take any 2 natural numbers and you multiply them together, you get another natural number. And if you add any 2 together, you get another natural number. So you could say that there was an algebra of natural numbers, and it had operators of plus and operators, and the operator of multiplication. But then you actually try and subtract one number from another. And that seems to work reasonably well, unless the number that you're subtracting from the first number is greater than the first number. So if you subtract 4 from 3, you get -1, and -1 is not a natural number. In fact, there's nothing in the world that you can point to physical that actually instantiates the idea of -1. -1's it's a wholly mathematical concept in that respect. So if we wanted to raise the algebra of natural numbers to include subtraction, then we actually need to have the set of integers that go from -infinity to +infinity in ones, you know. And then we actually would have a ground set to operate on with any operator that we chose out of plus, minus, and multiplication. And that's fine. And And what we just did there, what I'm talking to, is we raised the natural numbers to another algebraic level, and that algebraic level would be called the integers. But you take any two integers and you divide one into another, and you suddenly discover that some of them, the answer isn't amongst the integers. So you can divide you can divide 3 by 1 and you get 3, or you can divide 9 by 3 and you get 3. But try dividing 3 by 9, and all of a sudden you've got an answer that isn't in the integers. It's in the rational numbers. So you actually have to lift, in order to accommodate the new operator, which is division, you have to lift the set that you're dealing with from integers into rational numbers. They're called rational because they are all ratios, the rational numbers. And actually, you can keep on going up. You can go from rational numbers to irrational numbers. And if you include them, it's called the real numbers. And you can go from the real numbers to the complex numbers or the imaginary numbers. And each time you're doing this, you're enabling new operators, and you're actually lifting the algebra. Well, this is what's going on with data algebra. You start off with the basic definition of, I mean, I wrote a whole chapter as to why a couplet actually defines the basic unit of data, but it's a couplet. And we write it exponentially. Mathematically, it's written as if it was a to the power b. And all that indicates is that a and b are separate and distinct, but related in some way or other. So you could have, you know, a value at a given address in the computer, or you could have a value that had a metadata tag, like, you know, John and name, or you could have a value that had a data type, so it could be John and varchar or something. You can, as soon as you have a couplet, you can actually start creating the basic units that you would have within a data processing environment. And there's a couple of operators that you can use to operate on couplets. One's called composition, the other's called transposition, and I'm not going to explain them because you'll all go to sleep. We raise the algebra of couplets into the algebra of relations. This is the word relation as properly defined in mathematics. To get an algebra based on relations, and it just happens to be sets of couplets, right? But this is the point at which set theory entered in. There is no set theory in the algebra of couplets, but set theory comes in with all of its operators when we get to the algebra of relations. So you get union, intersection, complementation. And we also get the ability to do subsetting, and two specific operators that were defined for data called superscription and subscription, which operate between sets of relations. And then, having developed an algebra of relations, we raise it again into the algebra of what are called clans. And clans are just sets of relations, so that's sets of sets. So you could think of a table in a relational database as being a clan. Or you could think of just any kind of data set in any database anywhere as being a clan, because it will have, mathematically, it will have this form. It will be sets of couplets gathered together within sets themselves. It's sets of sets. And once you actually get to clans, there is an algebra higher than that called hordes, and the algebra higher than that is not even named, because there turned to be very, very little need to actually go there. If you actually define graphs, and this is in the book, but I'm not actually going to try and do it here, you discover that graphs are relations of a particular kind. You know, so once we've got to the algebra of clans, you're actually in a situation where pretty much every data structure that anybody deals with can actually be represented by this mathematical representation. And you know, once we got to clans, there was a need to introduce additional operators. They were called cross-union, cross-intersection, cross-superscription, cross, 'actually, I should say cross-subscription. There's an error. And they were introduced so that we could operate between clans in order to create join activity. They're specifically created for joins, those. And so that's kind of what has been done here, is that the basic mathematics is pretty much garden variety set theory based upon a specific unit of data. And then a number of operators, which if you hadn't called them operators, could have been defined as functions anyway, but a number of specific operators were created to actually do manipulations of the kind that you want to manipulate data with. And then, after a certain period of time and after an awful lot of effort, the guys at Algebraics came to the conclusion that the data algebra was complete. Once, if you kind of like get, you know, a clan is a set of sets. If you get sets of sets of sets, then that's a horde. I'm not defining it because there are no new operators that we need to be concerned about that go there. But if you want to think of what a horde is a database. A database is a collection of sets of sets. So a relational database would classify as would count as a horde, but so would a file system. A file system, individual files, for instance, an XML file, is very likely to be a clan. It's possible that an XML file could even be a horde, depending upon exactly how you do it, but you could transform it into a clan. You can, in one way or another, take these data structures and just move them into other data structures that are entirely equivalent one to the other. And that's how you mess about with data algebra, to be honest. I've probably lost you all in all of that, and my apologies if I have. I'm putting this up just to give an indication of what a join looks like. I'm really not going to explain this, but basically a join is the join between the clans A and B on the left is defined to be a superscription of the set of A composed by x to the x raised through a clan, and on the other side B the same as a cost superscription that applies only to F-Yang elements, and where X is an element of Yang A intersection Yang B, and F-Yang equals a relation element of the Cartesian product of the ground set, and R is Yang functional. And I'm really not going to explain any of that. I'm just saying that's a join. And once you've actually got a join, you've pretty much got everything that you would ever encounter in a relational database in terms of data algebra. Okay. Here's something that, and this hasn't been explored, but I'm sure that it's going to be explored. Mathematically, the whole of mathematics falls into set theory. It seems like a very odd thing. George Cantor, in about 1880-something, invented set theory. And a number of mathematicians, for decades afterwards, started to try and move all of mathematics into set theory. And all mathematics actually can be moved into set theory, with the exception of category theory, which itself subsumes set theory. So set theory, pretty much all the math you do is actually set theory. You just didn't know it and you didn't think of it like that, but it is. All of the numbers, for instance, have actually been, in one way or another, demonstrated to be a tower of algebras, and pretty much all of what you're doing, either with finite or what I think of as infinite, but calculus activity. What you're actually doing is you're playing with set theory, but you didn't know it and you never saw it, and nobody knew it until set theory itself had been defined. But the point about that is that set theory actually brings all of finite mathematics with it. I'm using the word finite here because the computer's finite and therefore data's finite, because the only data that we're interested in is in the computer. And all the computers in the world, although there may well be billions of them by now, they all can only contain finite amounts of data, even including all of the data that they have stored in various storage devices everywhere. It's all finite. And that actually makes a lot of things easy because it means you don't actually have to deal with the paradoxes that, or with the awkwardness that this number infinity seems to create. So if you take finite mathematics, that means numerical analysis, that means group theory, that means matrix algebra, that means vector algebra, that means topology, that means Euclidean geometry. All of that comes with data algebra. All of it could be represented algebraically. All of it can be processed as data. So the fact that there's a data algebra doesn't just mean that there's an algebra of data. It means that mathematics in all of its power can be brought to bear in the whole of the data space. And while it's absolutely true that an awful lot of it already has been, it's never been done formally on top of a data algebra. And there may be some things that come from that. My particular expectation is that group theory is going to make a huge difference to IT, but that's just a gut feel. It's been used in various ways already. Incidentally, it's been used for various forms of encryption, and but there are probably a whole series of areas where group theory can take effect as soon as you represent data algebraically, and that's yet to be seen because that isn't what algebraics were experimenting with. They were experimenting in a very specific space. Here's a book. If you didn't understand the thing I said, then maybe you would understand the book. It's been written for software developers, data professionals, and mathematicians, and that's why I was hired, because I have been both a software developer and a data professional and a mathematician. And the whole goal of the book is actually to try and explain the mathematics in as accessible a way as possible. I determined the contents in terms of marking out what would and wouldn't be in the book. And what was included in the book, basically I wanted to explain all the data structures that would convince people that data could be, data algebra could be applied to any kind of normal database and any kind of graph database. And, in passing, how it applies to XML, The book takes step-by-step approach to explain it. It's not your grandfather's math textbook. In fact, it doesn't read much like a textbook. It's not like any other textbook you come across. And that's really because there's been a very definite effort to be entertaining, knowing that this might be one of the driest subjects in the world if you wrote the book in a formal way. This is not written formally at all. In fact, I would guess, but nobody's even thinking about it right now, I would guess that there's going to be a data algebra textbook that emerges at some point in the future. And my guess is that I'll be involved in writing that. But at this point in time, that wasn't what we were trying to do. We weren't trying to have a formal global definition of data algebra. We're hoping really to introduce it. In fact, this could be subtitled An Introduction to Data Algebra.
Hey, we could do the old get the book, don't wait for the movie, right?
Yeah. And I'm
had to work that in.
I'm going to be played by Tom Cruise in the movie. It's already being negotiated. This is like the question, and a number of people have come to me and asked the question when I started talking about data algebra. Well, what difference does it make? We've had 40 years of software engineering without it. So what's different? And really the best thing, the best way to demonstrate this is like, you can say, mathematics creates an abstract field in which you can work, and it creates a global capability across that field of abstraction. And insofar as the field of abstraction can model the real world, it will improve anything that's being done in the real world that the model itself can represent. But that's just an argument. That's just this is what happened. There was a fair amount of mathematics that went on before algebra came out of the Middle East and landed in Europe. But this is the record, and this isn't the record of all mathematics. This is just the record of what was supremely valuable. Luca Pacioli invented bookkeeping. Bookkeeping, or double entry bookkeeping, was a mathematical idea that Pacioli came up with. And he included in that, from the get-go, not just double entry bookkeeping, but balance sheet, trial balance, and so on. The whole of that enabled the mercantile economies of the Renaissance and the centuries afterwards, and it enabled a capitalistic economy. Couldn't work without it, because there isn't any other way that anybody's invented of trapping money. Luca Pacioli solved the problem way back in 1494. In 1614, John Napier invented logarithms. We don't kind of care too much about logarithms anymore, but what he'd actually done is he found a method of doing multiplication via addition. And the initial thing was to create log tables so people could do multiplication. Takes a long time and people get it wrong. People could use log tables to actually do multiplication by adding numbers together, where people make much fewer errors and it happens a lot faster. Out of that came the invention of the slide rule, which was to put a logarithmic scale on a sliding ruler. And out of that came effectively pretty much the best engineering tool that anybody had until calculators were invented, which is, as it happens, calculators were kind of, well, didn't really appear until the 50s in any meaningful way. Blaise Pascal and Pierre de Fermat invented probability theory. So aside from gaming theory, which is one's mind immediately goes to that, provided the full basis for statistics, the whole of the insurance sector, and it has applications throughout the whole of science. Quantum mechanics, for instance, is an expression of probability theory and part of its implementation. That was 1654. And all that I did here was I just chose mathematical developments that have just proved to be hugely valuable. Isaac Newton, Gottfried Leibniz jointly invented calculus at about the same time. That's pretty much everywhere. All fields of engineering I've ever come across, it's ubiquitous in physics, operations research, statistics requires it, commerce, space exploration, all of it. Without calculus, you wouldn't be able to do it anything like as well if you would be able to do it at all. Évariste Galois invented group theory. That's used in modern particle physics, molecular physics, music, crystallography, material science, cryptography, error correction in computing. And actually, most people don't even know what group theory is, but it's an extremely powerful way of manipulating patterns that turn out to be mathematically identical, and finding things that are mathematically identical that you wouldn't necessarily think were mathematically identical. It's extremely powerful, and it has applications way beyond the ones I've mentioned. Alan Turing and John von Neumann together invented the computer industry. Mostly it was based upon the von Neumann architecture, but an awful lot of conceptual things in computing actually fell out of Alan Turing's Turing machine. And they're the foundation of the computer industry, which is not really a small industry. This is something that most people have forgotten. James Cooley and John Tukey invented the fast Fourier transform. It could be said that they invented it, but actually the truth is they rediscovered it. After they'd produced it, what it does is it allows you to speed up an awful lot of computing calculations, large integer multiplication, efficient matrix vector multiplication, filtering algorithms, difference equations, an awful lot of mathematics that goes on in the computer can be calculated within a reasonable level of accuracy by the fast Fourier transform. It's a kind of very accurate estimating process. After it was discovered and started to be used, somebody examined the notes that had been made by Gauss, the German mathematician, and they found as a kind of note in Latin at the end of something that he'd written. He just wrote out the fast Fourier transform. So Cooley and Tukey actually rediscovered it rather than discovered it. But the the impact, some of the calculations actually go 100,000 times faster because of the fast Fourier transform. So that's my list of things where mathematics made an impact. And data algebra, sole creation only of Gary Sherman, professor. It's been proven in data integration, data management, and query optimization. It's really hard to know where else it might have an impact. It may have, they may even be, you know, only a fraction of what it will actually do. But the situation is now that all data can be represented mathematically and therefore can be manipulated mathematically. We have, in a sense, the full capability of abstraction brought to bear on data. So, likely impacts. Well, data algebra provides a common language for all data. It would mean that if in one way or another, and I think this is probably going to happen, if in one way or another people started to want to standardize on the way that data declared itself, then they'd take something that's very much like XML, I think, and just express it algebraically. And remove a lot of the things that get in the way of XML. And you would have a common language for data. And that would mean that any piece of data stored anywhere could know what it was and declare its structure. And that would ease data integration problems across the board and across the world, you know. And the thing to say here is that think of data stores, you know, all file systems, XML files, databases of all varieties, document stores. Algebraically, these things are not distinct. They're the same thing. They are just algebraic data structures that happen to have values associated with them. And the way that we look at the world right now, a file system in the database is a completely different thing. And, you know, data in XML files, which are actually human readable, which is a nice thing, that doesn't look like how you would store data in file systems. And it doesn't look like, well, you can have XML databases, but it doesn't look like relational databases or even object databases. Document stores, and I mention these simply because there's JSONs around. And that's another way of declaring data. But it would be better for in all of these instances to declare it algebraically using the same terms. And I think that will happen. And when that happens, a whole series of what we thought of as data integration problems won't be problems anymore. The second thing I think it will do is it will harmonize data retrieval. With data retrieval, you know, file navigation, you're looking for a file, or you're looking for a file with something in it. Data retrieval languages, SQL, JSON, IQX, Query, Sparkle. Search, the searches that you do in various search capabilities, including the Google search, right? Algebraically, these are all the same problem. They're just it's just the axiom of specification against a collection of algebraically expressed data in actual fact. So there becomes a possibility of actually having a kind of universal query language that comes out of the algebra, but that's ways away. Now, this is, and I'll put this up, this is what algebraics have created, but it's an optimization capability, and I'll just walk through it swiftly. You put in, you know, if you start on the top left of the diagram, there's a translation layer that takes requests like SQL requests and gives back responses after the engine has done its job. The algebraic engine resolves it into algebra. It does a cost calculation. It has a memory of all the algebra it's done before, so it's got an algebraic catalog and activity log. And it takes the query and it answers it, but as it does so, it creates transitional results, and those transitional results are intermediate results. So, you know, you took a range of values out of a particular table. Well, it stores that range of values and the table that went, that part of the table that went through, and then you sorted it. So you, it stores a sorted version, and then you joined it to something else, so it stores the joined version. It just stores all the transitional results. And the next query that comes in, it looks to see if it can use the transitional results, which are, you know, partially calculated or even completely calculated to answer the query, in which case it doesn't need to go to all the data anymore. That's roughly speaking how it works. It can ingest new data. It can hold all of its data, so when source data comes in, it can create its own data. But that's basically optimization. I'm not going to say anything further about it because as soon as you go beyond that, it kind of gets a little bit complicated. So this is kind of a summary. In time, we expect standards to be developed for data declaration and data retrieval, and for the reasons that I've said. We're going to do data algebra training. We've no idea if there's going to be a large requirement for this, but anyway, I've been working together with Rebecca Jos. We have a training course partially created. Any companies that like to train their staff in data algebra at any point in time, contact Mary Jo, not at the Bloor group. She'll, I don't know, she'll tell you, or try and arrange for us to do it. Algebraics themselves are created in an algebraics library that's built in Python. What this does is it uses the Python language to instantiate the mathematics so people can play with the mathematics in Python. It's only going to be interested to developers that know Python, I guess. It can be downloaded along with a PDF of the book, and we've got the URL there. And this is my final thing to say: an invasion of armies can be resisted, but not an idea whose time has come.
Yes, indeed. And Robin, I think I lost you. Are you still there?
Yeah, I'm still here.
Okay, sorry, your audio just cut out there. As you were talking about this, especially the layers of algebras, I couldn't help but think about the inimitable T.S. Eliot in his old Possum's Book of Practical Cats, where he talks about the cat. He refers to a cat sitting there thinking, and you can't help but believe that he's considering the thought of the thought of the thought of his name. And, of course, layers of abstraction, right? So that's a pretty good metaphor for what you described, right?
That's exactly right. Yeah.
Yeah, this is very interesting. So something else I'll just throw out there. We have a couple of very good questions from the audience. But as I'm considering all of this, it seems to me, correct me if I'm wrong, that the power of a data algebra really comes into play during that computational component of the equation, meaning executing queries, for example. But the hard part, the nitty-gritty, really is representing your data algebraically. So that's why it works so well at optimizing SQL, because with SQL you have a limited set of elements, if you will, and functions or operators. Is that right?
Yeah, SQL has its own operators, most of which are actually arithmetic after, algebraic after a fashion, and therefore they can be translated straight into data algebra.
Yeah, that's very interesting stuff. We have a bunch of really good questions from the audience. Let me just kind of dive right in. Here's one I'll just kind of throw out at you for context, I suppose, because at the end of the day, obviously, you need people to use all this stuff, and you need the business to understand what it means and to leverage what it means, and you need to look always beyond the data, really. And one of our attendees threw out an interesting comment that Nazi Field Marshal Rommel memorized log tables as a fun fact, and then I mentioned that movie, Inglourious Bastards, in which the main character has this great line where he says, he's asking the Frenchman if he knows of any Jewish people in the region, and he says, oh, you know, only rumors is all I know. It's about some particular group of people. And he has this great line where he says, oh, I love rumors. Facts can be so misleading, but rumors, true or false, always provide valuable insights. And that always kind of, it always cracked me up because he's talking about looking beyond the numbers and appreciating the gravitas of whatever situation you have and whatever you learn. And I guess he's also pointing out that sometimes you really have to work your way through which function you're going to apply to these sets that you have in set theory, right? It's not, the thing about math is that, especially with algebra, people think, well, math is so concise, it's so concrete, it's so specific. But when you talk about algebra, and of course algebras of algebras of algebras, well, now you're getting into a very interesting, nuanced space where you do have to apply some creative thinking to achieve that elegant answer. Is that about right?
Well, I think that's true. I think what will happen, though, is that mostly that will be done at an architectural level by people who are conversant with the math. You know, I don't think that you'll have individual programmers doing it. I mean, you know, there's something worth saying here that maybe I should have said in the presentation, but it's like Alan Turing demonstrated, in effect, that you could reduce all computers to Turing machines. In effect, you know, he pretty much defined the limits. That meant you could express all processing mathematically, but he never worked upon the expression of data mathematically. If you put those two things together, then it's possible, although I think this is a long ways away, it's possible that actually computer programming would eventually become nothing more than mathematics. In other words, it would just be doing mathematical functions against mathematical objects.
Right. Well, good point. It's very interesting. And again, it comes down to all the legwork required, to represent your data algebraically, but then also we have an attendee asking, okay, this is great conceptually, but how does it apply to the real world? And to kind of answer that, I'm leading you down this path that A, you have to algebraically represent your data, and then B, software developers for various applications need to come up with some way to leverage this. And I've always kind of wondered, since we've been talking about this, are we really talking about what metadata always should have been? Is that kind of the role? Because metadata, of course, is a layer of abstraction. So could the algebra of data essentially fulfill the long-sought yet elusive promise of metadata?
Well, most of the problems in metadata have actually been solved in terms of, so, you know, if you actually have a well-designed ontology that relates metadata tags to each other and the nature of their meaning, then you can, in one way or another, you know, an ontology is just another algebraic structure, as it turns out. You can submit data to a computer that is inadequately specified. In other words, if you actually didn't put any meaning on a piece of data, it absolutely has no meaning. You know, what has actually been done in computing for decades is that the meaning of the data was held in the program, and the data itself was held on disk or in some storage format, you know. So the program was storing the meanings of the data, and really that's now that there's an algebra of data at least, that's no longer necessary, and the program could pick up that information if it wanted to, you know. The data could declare it itself. That wasn't previously possible, but it doesn't get over the fact that there's going to be, you know, exabytes of data out there that don't have well-specified metadata, and there really isn't going to be anything for it but in one way or another to find a way of applying metadata to it if you want to be able to process the data meaningfully. You know, I mean, there's a whole series of what we call errors in computing. That's, you know, like, that's just one of them. It's that in one way or another the data has been allowed to run wild without applying formal meaning to it, and because of that you've got a lot of wild data out there that nobody is exactly sure what it means.
That's funny. I remember you once said data doesn't know what it is, but of course in certain texts that's not entirely true. But still, okay, we have several other great questions here. So I like this one. An attendee asks, does data algebra have provable closure? In other words, any set of operations on a structure in data algebra leads to another valid structure in data algebra. I happen to think the answer is yes there, right?
Well, yes, it does have closure. That's actually, that would be the point of raising from one algebra to another. You would actually have to have closure within that algebra. In other words, you couldn't have any operations on any collection. Given that you've got the base set or the genesis set that you generate the data from, then the answer is going to be in a data structure that's derived from the genesis set, basically. So yes, it has closure.
And, you know, I remember, I can actually see the room right now where you and I sat in Austin back in, whatever, 2010, and we were watching as queries were put into what algebraic data had, of course, way back then, which is before the algebra of data. And we watched as the optimizer would go from the first query, which was, let's say, a minute, the second query was like 7 seconds, third query was a second, and the fourth query was sub-second. And I'm guessing that what's happening is somewhat related to what we're talking about today, meaning that it is an optimizer, to the point of one question we had from an attendee. It is an optimizer, and what it's doing is applying different algebraic functions over time, and then, of course, measuring those. But because it's abstracted the problem out so elegantly, it's able to achieve those optimizations much faster than what we would traditionally think about with a optimizer from relational database. Is that right?
Well, yeah. The way that this works is it's best to think of it as data reuse. You could do a TPCH benchmark. I mean, they did, you know, early on, did a TPCH benchmark. The first time you run it, you get the answer in a certain period of time, and I think the way that software that they were building at that time, I think the way that ran, it didn't run particularly fast. But the second time you run it, you get the answer instantly because you already had the answer, and it will have saved the answer. So it made any kind of benchmark not doable, because as soon as you run the benchmark, when you run it again, you've already got the answer. So all you're doing is reading the answer from disk, you know, or reading it from memory if you kept it in memory, you know. So once you actually have an optimizer that depends upon data reuse, the reason that this couldn't be done in the way that's been done here is that the algebra allows you to define every data structure you created as an intermediate result, and therefore it can know what intermediate results exist, and it can mathematically deduce whether it can use any of the intermediate results. And that's why it gets faster. I mean, the more queries you run on it, it gets faster because you've got more intermediate results to do. The other thing that happens, of course, is that you keep on doing this, then you end up with an awful lot of data, and then it starts throwing away the stuff it doesn't want. But what it's actually doing, and this is kind of why it's kind of important in a way, is it's trading CPU for slow storage. Basically, you will use much less CPU, but you can let the storage expand as much as you want, and storage is inexpensive and doesn't require much cooling, and CPU is expensive and it does require cooling. So in a way, one of the things, you know, you don't necessarily need to think of this as making stuff go faster. You can think of it as actually just decreasing the cost of operation.
Yeah, that's a very good point. This is such interesting stuff. So here's another fantastic question, and folks, I think I'll read one more, and we'll let you go. Again, noting that we will do some classes, probably in Austin first, but then if it takes off, we'll certainly move around. But this is a great question that just came in. So one of the attendees writes, so data algebra deals with the abstract structures that encompass values. Isn't most of the overhead data processing actually getting values in and out of structures, in other words, mapping and storing values, the point being that the structural algebra plays a lesser role? He writes, I'm no mathematician, so the question comes from a crude intuition regarding what I've heard you say. But he's kind of talking about how do you actually get the values into the algebraic expressions, which is a sufficient point. Can you kind of speak to that? This is back to, so this is like what I was asking earlier. The difficult part is representing your data algebraically, and I guess that's what the library does, what you talked about. And folks, this is open source, meaning you can go up here and check that out. It's on GitHub, as I understand it, so you can check out the Algebra of Data itself. But do you see his point that you do have to represent it first algebraically, and then all the magic happens, but until then, none of the magic happens?
Well, I mean, the first thing to say is if you're reading data into any piece of software, right, if you're reading data into any piece of software, you might have something like a CSV file. You might just have a string of bits which some program knows about what those string of bits mean. So it might actually be a JPEG or whatever. But you know, the software doesn't know about it. As soon as the software applies any structure, and it's going to, because that's the first thing that software does when it reads data in, is it opposes a structure on it. At that point in time, you have an algebraic structure. There isn't any form of data that can't be represented algebraically. You know, if you've got 3 ints in a row, right, so short integers in a row, you know, what you've got is 3 ints. You know that you've got 3 ints because the program tells you you've got 3 ints. You don't know anything else about that data other than the address it is, so that's another attribute that you've actually got. But the data algebra just does that. I mean, it's just like, it's in one way or another, as soon as you declare structure, it can represent the structure. It can represent any data structure. That's the point, you know. If the data is really messed up and people have not put in the information that they should have put in order to recognize it, then the algebra isn't going to help you recognize it. It's just going to declare the structure. You know, the beauty of the structure is you discover that there are various algebraic transformations that you didn't think that one specific thing was entirely and completely equal to another, that you discover just by doing various manipulations. Oh, this is the same as that. You didn't know, right? And you didn't know because one particular data structure is, maybe it contains all of the values that you have in some other particular data structure, but it looks entirely different, you know? The algebra just finds the equality in all of those things, and it removes some of that issue, you know. But you know, the point is really, if you think about what was intended with SQL, was that you'd be able to do things declaratively. You wouldn't actually have to tell the database what to do. You just say how to do it. In one way or another, pretty much all algebraic operation on data is declarative. It says take this, transform it like this, and this is what you get. You know, and it isn't insisting that a computer do that in a particular way. However, if it hasn't got software underneath it that can recognize the instructions and do it, then it's not going to be able to do it. You know, you're going to have to, in the same way that you have an optimizing relational database that begins with a parser to work out what it wants, you're going to have, in one way or another, whatever algebraic structure is, if you actually solve the problem in algebra, unless the language is itself entirely algebraic, you're going to, in one way or another, have to code what the algebra does. But it's still declarative. It's all declarative.
Well, folks, that is fantastic stuff. We burned through more than an hour. We will have more on this. Watch for it. We've learned all about the algebra of data, folks. We'll talk to you very, very soon. And thanks again. Thanks, Robin, for writing this book. You can find information about it in our newsletters, I am sure. Go on insideanalysis.com. We'll get some information there. And I'm pretty excited. I think it's a pretty big deal. We do need, of course, software companies to embrace it. We need standards to be set. We need people to learn about it and to take it to the next step. This is just the concept. It's the abstraction, but it is a beginning. And, folks, we're going to leave you with that. We'll talk to you next time. Take care. Bye-bye.